So the last speaker of this morning session is Professor Eduard Looijenga from where now is Utrecht University, right? I think Professor Looijenga has been at Tsinghua since 2013. So he's an expert in many areas of algebraic geometry. So I guess too many areas. In any way, so let's welcome. Okay, yeah.
Yes, thank you for the introduction. Actually, my current affiliation is Chicago, where I'm a long-term visitor. Yeah, I also want to thank the organizing committee for inviting me. It's an amazing place in more than one way. The setting, but also this institute. Came into being in 3-4 years, and it is really stunning. The topic of my talk is interplay between a chapter in algebraic geometry, Ball quotients, and the theory of sporadic groups. Now, Mumford, when he wrote his red book on algebraic geometry, introducing the rest of us to a Grothendieck-style algebraic geometry, says somewhere in his introduction that it was believed that the Grothendieck school was secretly plotting to take over all of mathematics. Well, that didn't quite happen, and it certainly did not include the theory of sporadic groups. But I want to show you today that even algebraic geometry can make, it's not going to take it over, but it can make contact with the theory of sporadic groups. Now, finite groups have already occurred in algebraic geometry for a long time as Galois groups. And the geometric setting in which this appears is that you have some thing that parameterizes something like universal family, parameterizing hot structures, and then the monodromic group of that situation is often of an arithmetic nature. And if you then take finite Galois covers by introducing level structures, the kind of groups, Galois groups you encounter in this way are usually Chevalley groups, interesting by themselves, but by no means sporadic. Now, a quarter of a century ago, Daniel Allcock made a conjecture that implied or suggested that there ought to be a link between algebraic geometry and the monster group. And so that is the topic of my talk. It is not a solution of that conjecture, but it goes quite far in that direction. And I take the occasion to introduce you to the notions that underlie it, like a ball quotient. So let's begin in a sort of elementary fashion. So I first explain to you what a ball quotient is, or recall what it is. So let W be a complex vector space of finite dimension and endowed with a non-degenerate Hermitian form. Which I is supposed to be to have Lorentzian signature, which means that the signature, well, hyperbolic signature is also the term of type. And well, if that's the case, then you can find a basis for which this takes the standard form, and if a set of coordinates corresponding to that basis is denoted like this, then we can always arrange that the form is given if I substitute, take the same variable, and take the same argument, that it looks like this. And this defines a complex ball simply by taking the locus of points where this is negative and then projectivizing. So I look at the points where this expression is negative, and of course this being negative you can use affine coordinates corresponding to the system, then it just means that you're asking that this inequality is satisfied, and that's indeed the inequality that defines a complex ball. This is all canonical, clearly. So, for instance, the unitary group of W is acting on that ball. Let's give this ball a name, or let's not a name, rather a notation. I will stick to this type of notation for a ball. And the unitary group of W is acting on it. And in fact, that ball is a symmetric space for this group. It's a reductive group, not a semi-simple group, but never mind. The stabilizer of every point is a maximal compact subgroup here. The action is transitive. That's basically what characterizes this. And now if we have a discrete subgroup, let's call that gamma, which is what is called a lattice. So this will be discrete. And to ask it to be a lattice means simply that this is of cofinite volume. If you take the quotient of gamma by this, then the volume should be finite. You can also say if you take the quotient of orbit space, the gamma orbit space of gamma in here, then it is a finite volume. And then it's the fact that if we take the orbit space, we should actually think of it as an orbifold, has more structure. A priori, this is an analytic orbifold, but it is in fact a quasi-projective orbifold, and that is a consequence of the Bailey-Borel theory. So this recalls the notion of a ball quotient. This is what we call a ball quotient. Now these ball quotients appear in algebraic geometry a lot in interesting fashion. And so let me explain how they do appear. You may ask, for instance, how do you get a gamma like this? And they often arise as for Eisenstein lattices. So let me recall first what the Eisenstein ring is. That's quite simple. That's just the ring of integers of the third roots of unity. So it can be defined like this. This is the minimal polynomial for this omega, and you can embed it in C by sending this omega indeed to the first root of unity. There are two such embeddings, of course, and the image is simply this. So I have identified this, in fact, with a lattice in C. Now, a Lorentzian Eisenstein lattice, or hyperbolic Eisenstein lattice, if you like, it's not a lattice in the sense I used here, but in a more elementary. So that is a free E module over the Eisenstein ring of, say, a rank m+1, which has the same kind of signature as we have here. And once you have such a E module, let's give it a name, script L, then we can complexify according to this embedding. So we can take our W, the W that appears over there, this tensor product over the Eisenstein ring of that Lorentzian lattice, that will produce a vector space equipped with a Hermitian form like this, and it will lead you to a ball. So that ball I will denote now by BL instead of BW. So that's by definition the same thing for me. But this approach automatically leads you to a gamma, because we can take for gamma the unitary group of that lattice. So we take just the unitary transformation that preserves this, and that gives you indeed a lattice in the sense as I used it here. Right? So this is we can sort of take the quotient with respect to that, and then the notation that I will use is that I will simply write x of L for the corresponding quotient. So I take this gamma. So that's one particular ball quotient that you associate to such a Lorentzian Eisenstein lattice. Now, I still have not explained to you how they arise in algebraic geometry, so that's what I will do next. The statement is that these are, in fact, have the structure of what is called the Shimura variety. Shimura varieties are known to parameterize Hodge structures. So I'm going to tell you how such a ball quotient parameterizes Hodge structures. So for that, let's start with an ordinary integral lattice. So free Z module, say of rank twice the rank over here, 2n plus 2. And let's assume that this Z module comes with a pairing indicated by a dot, symmetric, bilinear, non-degenerate. And of signature 2n, 2. Now, before I discuss any ball quotient associated to it, let me first tell you how such a lattice determines a Shimura variety of what is called orthogonal type. So what we do is we consider, so that's basically the analog of the ball that we have over here, a domain DL. Well, it's not quite a domain, it's not going to be connected. Each connected component is a domain. So we take the elements in the complexification of L, for which Z dot Z is 0. So I have extended the dots product in symmetric bilinear form to the complexification in the obvious way. So this means that this lies on a quadratic, but I also want to satisfy an inequality, and the inequality is this one. This has, if you see this for the first time, then it's hard to imagine what it is representing, but let me make one comment. This is almost, this has, as I said, two connected components, and each connected component can be identified with the Grassmannian of positive definite two planes in the underlying real vector space. So what you do is you take a Z in here, and you could associate to Z, well, the span of its imaginary part and its real part. And so that is in the real, underlying real vector space, a positive definite two plane. And the map restricted to a connected component to this Grassmannian of positive definite two planes is an isomorphism. The one bit, literally one bit of extra information that you have in order to separate connected components is basically the orientation of that tuple. This, each connected component is a symmetric space for the orthogonal group of LR. So I should say it like this. The orthogonal group of the underlying real vector space acts transitively on the L. And the stabilizer of a point is maximal, it's not up to a finite group, maximal compact subgroup. So stabilizer of, that looks like this. It's SO2 cross O2N. Maximal compact, it would be without the S. So the orthogonal group of L itself acts nicely on dl, and it has an orbit space which is also again quasi-projective, as it could have two connected components. But what I'm interested in is the situation where we are given a structure on L of an Lorentzian Eisenstein lattice. And such a structure is simply given by an orthogonal transformation which satisfies this kind of Eisenstein equation. So for which we have rho squared plus rho plus 1 is equal to 0. Because that is clear that if you let omega act as rho, then we get L gets structure of Lorentzian Eisenstein lattice. Well, a priori, it gets a structure of an Eisenstein lattice, L, but it's going to be of Lorentzian signature, and there is indeed the Hermitian form, H, which has the following property. It takes L cross L to, well, theta cross L. Let me tell you what theta is. Theta is by definition, let me just do it in a picture. So here we have 0. This is a complex picture in the complex plane. So here we have omega. Then there is a primitive sixth root of unity that's minus omega squared. And the sum of these two, so that's omega minus omega squared. That's a purely imaginary number, and that purely imaginary number is just the square root of minus 3. And you land in this because I can write down H in a very explicit manner. It's given like this. It is A dot B minus omega A dot rho B, and then you have to multiply this with this theta. That's how this associated Hermitian form is defined. And so that produces this B of L, and that B of L is in fact sitting in the domain, connected components perhaps, of the domain that I introduced, not these. So, say it again. Yes, I think, sorry, yeah, thank you. Yeah. This is what I meant, okay? Sorry? I think it will be fixed point free automatically. because it will have the eigenvalues of rho are necessarily omega and omega bar, right? And so this B of L is actually sitting in the locus where is actually equal to the locus where rho acts with eigenvalue omega. Now, so this is what I would call the a characterization of such a ball as parameterizing hot structures. How does that work? So let me do that first. For the domain dl, how is dl parameterizing hot structures? Well, let's take an element there. Then I'm going to associate to this a hot structure of weight 0. And so the H1 minus 1 part is in fact just the span of Z. It's a one-dimensional subspace of the complexification of L. And then it has to be so that its complex conjugate also is part of that hot structure. And that's, you get, of course, by exchanging the two indices. And then the rest should be of type 0, 0. And the rest is you take just the direct sum of these two. And then the orthogonal complement with respect to the form. So that's a hot structure. And that's polarized, in fact, polarized by the given form. These are the linear algebra objects that can occur in algebraic geometry. And then in a situation like this, so this, as I said, this is viewed as a parameter space for such hot structures. And this ball inside it parameterizes hot structures for which there's an additional amount of symmetry. So this has, so BL, additional symmetry. So let me say just the symmetry of the group of order 3. Well, these, I claim, these are ubiquitous in algebraic geometry. They appear a lot. And I'd like to give one very important example. There are many other examples, but most of these examples are somehow related to this one. And it's the following. It appears in algebraic geometry as describing the moduli space of smooth cubic threefolds. Now, what is a cubic threefold? It's simply a smooth hypersurface in P4 given by a polynomial f of degree 3. Let me write capital F here. It's supposed to be smooth, so the partial derivatives have only the origin as the zero set in common. So that's a smooth cubic threefold. And as you can imagine, that has been the subject of a lot of investigation in the past century. Now, one way to investigate or to characterize Z up to a projective linear transformation is to look at its hot structure. But here it is more effective to look at the hot structure of Z, but of fourfold, a cubic fourfold that is associated to Z, and that is obtained by actually replacing this equation by this equation. you introduce an extra variable like this that defines something in P4, in P5, and so that's a smooth cubic fourfold. And geometrically, what we did here amounts to the following. We just looked at a branch cover of P4 that ramifies totally along Z. So we have here this cover with Galois group U3, and this group acts right there, right? It multiplies that coordinate with the third root of unity, and that's how this defines that action of Y. Now, the hot structure of Y is essentially of the type that I described here, or at least the interesting part of Y is of that type, the so-called primitive cohomology. So what you do is you take the cohomology of the ambient space, P5, that is cyclic, rank 1. It sits, it embeds in the cohomology of Y, and then we take the perp of that in here, that's a lattice, but the lattice is of the type that I described here, the type L, where the n is in fact 10. And so the action that I have from the generator omega gives me a row satisfying that Eisenstein equation, and so that action makes this a Lorentzian lattice of the type over there. So gives an L of rank 11. Hence a ball of dimension 10. And it is, of course, you're happy with the fact that this is also the dimension of the number of moduli of Z, and indeed, major result here, which is due to Allcock, Carlson, Toledo, and independently by me and a student of mine, which says that this construction assigning to Z this hot structure, or rather the element that corresponds to the ball quotient that we get in this matter, is in fact an open embedding. And so this produces a map from the orbits. Maybe I should not write here because it becomes not visible. So what we get is a map from the, say, the GL, what is it, 5C orbit, 4 orbits. Maybe I should do it like this, projectivize of such Z that maps to the ball quotient that I described there, but, well, we must divide out by the unitary group, so let me write it like this. But this map is in fact an open embedding. Sorry? No, I begin with a cubic. No, but the PGL4 is acting Am I mistaken here? Okay, probably, yeah. You're right, okay. This is a very consequential mix-up. Well, you are able to make the substitutions. Thank you. Yeah, sorry about that. Okay. So that gives me an open embedding. And the complement actually can be described in precise terms. And there's something interesting going on there. And it's worthwhile to spend a little bit of time on that because it also helps you to better appreciate the Allcock conjecture that I will state later on. So that requires me to discuss a little bit the discriminants that are associated to this construction. Open embedding complement a discriminant. And I will now explain what I mean by this. So for that, I want to go back to the situation right there. So let us take an element in, let's make also an assumption here, because that is, it's not necessary, but that is convenient. So assume L even, which means simply that the self-product of any element is even. But I want to consider the case where this self-product is 2, and we may call this a root. And such a root defines a reflection in the usual manner. So you get an element, orthogonal reflection. It preserves the lattice, and is simply defined by sending x to x minus alpha dot x times alpha, right? So this is a standard picture. Sends alpha to minus alpha, fixes a hyperplane perpendicular to it, and preserves the lattice. Such an element preserves every connected component of dl, and the fixed point locus isn't basically of the same type as dl itself, because you can see that it is actually the d that is associated to the fixed point, well, hyperplane intersected with the lattice of S alpha. So it is sitting inside this domain as a hyperplane section, but it is at the same time totally geodesic. So that's one of the wonderful properties that this class of domains have. Now, and this is always going to be non-empty. So it's hard to sort of picture. So let me make a very schematic picture. So this is the DL. This looks like this. So this is the, but these various hyperplane sections, they, of course, there are an infinite number of them. They intersect each other, but the way they intersect is locally finite. So it's like an arrangement, right? I'm not going to draw an infinite number of these hyperplane sections, but if I focus myself on a point, a given point, there will be only finitely many of these passing through them. So that makes it what it's called an arrangement. So they form an arrangement. And the way they intersect is locally pretty well understood, because they meet like a hyperplane arrangement, the hyperplane arrangement, or the reflection hyperplane arrangement, of a root system. And it's a root system where all the roots have the same length, right? All have length 2. So that is necessarily a root system that decomposes as a direct sum of root systems of type A, D, and D. Well, if you form the orbit space with respect to the arithmetic group that is relevant here, so if we divide out by, oh, well, I think I can erase this now. Say that again. This here? This is just an yeah, for all A in L, for every vector in L, I ask that A dot A is even, right? That's the definition of Niederlandes. Okay. So if we form this quotient by OL, then, well, there is necessarily a ramification along such a hyperplane section. And so there is this union of hyperplane sections that defines, at least is going to be part of the discriminant. So there's, in the discriminant of this map, and there's a little bit of a question how you define the discriminant. You can say, well, it is the points with non-trivial stabilizer, but then this is a kind of ramification locus that is not necessarily of pure codimension 1. So let me define the discriminant as something that is of pure codimension 1, the part for which these stabilizers are, for which the ramification is of codimension 1, and then this is the full discriminant. The discriminant is the image of this arrangement. Now, what about the situation when we when we restrict ourselves to the ball? So, if I have in alpha, for which a row of alpha makes up with alpha a root system of type A2, so it would be look like this. Here's alpha, here's a row of alpha, and of course then you have here a row squared of alpha, sum ought to be 0. Then this is an A2 root system, and we can then form T of alpha as the composite of 2 reflections. And that composite of these 2 reflections, that's an order 3 transformation, which respects the Lorentzian structure. So this actually is, so this is an order 3. And this is actually an element in the unitary group of the associated L. And it appears, and it is of course acting as the identity on the orthogonal complement, so this is indeed a complex reflection. And so such a complex reflection is going to be part of the discriminant when you pass from B of L to X of L. X of L, I recall, is just the orbit space with respect to the associated Lorentzian Eisenstein unitary group. So this here contributes to the discriminant. Now you would like to say something similar as I did here. These the fixed point set of this d alpha will actually define inside my B well, it's BL, a fixed point locus T alpha, and that fixed point locus is again a hyperplane section, but now in this complex vector space. The balls have in common with the domains that are discussed here, these are orthogonal domains, is that they admit these codimension 1, well, totally geodesic subdomains, and that's how you get them. And same story as over there, so these, you will have an infinite number of them in general, but they intersect in a locally finite manner, and you would like to understand how they intersect, as we did over here. Now here's an interesting parallel story, and that story is due to Allcock. He noticed this. So let us write L to I, or I is equal 1, 2, 3, and 4, for a root lattice of type, well, A2, D4, E6, and E8. So the rank of the root lattice is exactly the index that appears here. These root lattices stand out from all others in the following manner. They admit an order 3 transformation, which satisfies the Eisenstein identity. That is all at the same time a power of the Coxeter transformation. So these contain the Wow group, I should say, the Wow group contains a natural conjugation class of rows as before. Meaning that up to isometry, there is a natural way to turn this lattice into a Eisenstein lattice, not Lorentzian, but of positive definite. Turns L to I into what I will call Li. That's why I used the index even, so this is still for out 1 to 4. And well, you can complexify so that you get the complex vector space of dimension I, call that Wi, on which the orthogonal group, or the unitary group of Li is acting. So acts here, but that's going to be a finite group because it's positive definite. And indeed, it's a group generated by these 3 flexions. It's one of Shepard-Todd type. And the Chevrolet theory then tells you that if let's give this, it's abbreviated like this, that this is actually even an affine space. So this is isomorphic to Ci. Now that has a discriminant, of course. The image of all these reflection hyperplanes. Now these are the complex reflection hyperplanes with respect to an order 3 transformation. And that discriminant is actually a very familiar one. That discriminant is also the discriminant of just the symmetric group on I+1 elements. So this is isomorphic to, say, Ci divided by, this is the standard representation of Si+1. You can read here also the Wow group of type AI, that's the same thing. So that discriminant doesn't bring anything new, but it tells us something of interest, namely that there is also this cover, the implicit cover, by Ci with this covering group, yielding the same discriminant. So that describes, well, I should make that as a statement. So the claim is that the role of A, D, and E in this orthogonal story is taken here by these four cases. So these, this ball arrangement is locally like a complex hyperplane arrangement that decomposes according to the hyperplane arrangements of the types that I described here. So these play the role of A, D, and D. Okay. Right. I think I'm now, let's see how we're doing. Yeah. I am now ready actually to confront you with the Allcock conjecture and what can be said about it. So Allcock, as I said, almost, well, certainly a quarter of a century ago, he came up with an extremely interesting ball quotient. And that is defined as follows. So here we take for L the following lattice. We let L be an even unimodular. Unimodular means that the matrix of inner products has determinant plus or minus 1. Lattice of signature 26, 2. This is the standard theory of lattices tells you that this lattice is unique up to isomorphism. For instance, you can take 3 copies of an E8 lattice and then 2 copies of a hyperbolic lattice. You can take a copy of the Leech lattice and 2 copies of a hyperbolic lattice. There are many ways of getting it, but it's unique up to isomorphism. And then Allcock noticed that we can give this the structure of a Lorentzian lattice, Eisenstein lattice. There is a row in OL which satisfies the Eisenstein identity, and the row satisfying that identity, there are many of them, but they make up one conjugacy class in the orthogonal group. And that means that the structure that I get then on this L as a Lorentzian Eisenstein lattice, L, is actually also unique up to isometry. And in that case, we have, well, it is of course of signature. You have to look, well, this is 26.2. We must divide by 2, so the signature is going to be 13.1. And so what you get is a ball, BL, of dimension 13. And now Allcock and Baysack, so let me write down these names. They work together, and there are also individual papers by them, but sometimes improving over previous results. They showed that the whole unitary group of L is generated by the triflections. Now I'm using terminology that I did not properly introduce, but I follow Allcock's terminology, he calls this a triflexion. So let me do that too. This is generated by triflections. And these triflections also make up a single conjugacy class. So what one can do then is form that quotient B of L. Remember that if I pass through the orbit space with respect to the unitary group, I denote it in this manner. So L, I would refer to this as the Allcock Ball quotient. And the fact that I mentioned to you is namely that this is not just generated by the triflections, but that they make up a single conjugacy class, implies that the discriminant of this map is in fact irreducible. And Allcock observes more about this discriminant. He shows, using the work of Borchers, that this discriminant is also the zero set of a particular kind of modular form on BL, which is of even weight. And I will not write that down. Because I only want to exploit a geometric consequence of that fact. And the geometric consequence of that fact is the evenness of that weight, is that there exists a double cover of XL, which ramifies along that discriminant. So, in fact, there exists a double cover let's call the double cover X hat of LP, which has this as the locus of ramification. Okay, this is all a construction which, well, interesting, moderately interesting perhaps, but what makes it really interesting is the conjecture that he made. So that's Allcock. Namely, that the fundamental group of this double cover, it should be actually taken in an orbifold sense, is isomorphic to a product of the monster group with itself. So M stands here for the monster, that's the largest finite simple sporadic group. And you should do two copies, get two copies, and where do the two come from? Well, we have here a double cover, and that means that this appears actually as the quotient by taking under an involution, let's call it involution iota, and that involution actually should just exchange these two copies. If you do it on this level, then it would produce what is called the bi-monster, so that's a semi-direct product of the cyclic group of order 2 with M product, so weak product. Okay, but yeah, this is already, I think, very exciting conjecture by itself. But well, Allcock suggests more should be going on, and I suggest in particular that there should be something like a modular interpretation for this space and for this double cover. This is an example, as any Ball quotient, of a Shimura variety, and Shimura varieties parameterize Hutch structures. Although the question is really, is there a geometric origin of this Hutch structure? Is there some geometric object whose universal family produces this? And that of course, should bring in the monster group in an interesting manner. Well, Allcock and Basak I proved last year that either his conjecture is true or the situation is uninteresting in the following sense. So if conjecture fails, so let me state it in this manner. If the conjecture fails, then this double cover is simply connected. So there are only two possibilities. And now the result I want to close with is sort of an indication that this uninteresting case is not going to happen. There's no proof, but it's likely not to happen. And what is the result here? Well, remember that earlier in my talk I discussed this this Ball quotient parameterizing cubic threefolds. So let us write MCT for the moduli space of cubic threefolds that embedded in Ball quotient as an open subset of dimension 10. But that Ball quotient appears in the Allcock's Ball quotient, and it appears, well, I should be careful, I will not write this as an embedding, but as a sort of finite degree 1 map to its image. So this goes to B of L, so this is the 13-dimensional Allcock ball. And the way that arises is you take in here a root system, well, an L3. So you take an L3 in our L, that's the 13-dimensional lattice that I just, that's 14-dimensional, sorry, 14-dimensional lattice that I just defined. So this is positive definite. Right, that's how we did it. This is Lorentzian. And the perp of that is then Lorentzian also. And it has the kind of signature that we encounter here. So this is of signature, what is it, 10.1. And so the statement is that this maps, this image is the image that you get this. So you, image, so you get this map from this 10-dimensional ball to this ball with the image described in this manner. And that map, I said, it is not quite an embedding because it will get self-intersection. You get loci like that, not just simple self-intersection, but also very high orders in self-intersection. Now, the claim is, so 1 minute, I think? 2 minutes, okay. I can pronounce a sentence in these 2 minutes because that's actually what all I need to do. The claim is this, that the image has a tubular neighborhood. Let's call that neighborhood UCT for cubic threefold. So I take the closure, right, of that image here. So this Ball quotient, so it looks like this. And but we're sitting in the. I should have been better. So I should have been written here, this, right? Not the B, but the quotient. So this is the picture in that quotient. And the statement is, so let's go back to here. We have this P here. The claim is that if I take the pre-image of that neighborhood, then this has precisely the fundamental group predicted by Allcock. It's M cross N. And so the suggestion here is that, well, even if Allcock's conjecture is not true, there should be near these locus that parameterizes cubic threefolds, there should be objects that also have an algebrogeometric interpretation, and that makes that somehow this monster comes into the picture. Well, I want to close here. Thank you.
Okay, so questions, comments? Yeah.
You said that it is not a fundamental group, but the orbifold fundamental group.
Say that again?
You said that phi1 of X check is not the fundamental group, but it's the orbifold fundamental group.
An orbifold fundamental group, yes. Well, there will be, you allow ramification in codimension at least 2, right? There will be quotient singularities. And you must allow these quotient singularities to disappear by taking a finite cover, because that's all. If you like, if you prefer that language, it's the you can think of it as having the structure of a stack, the Linear-Mumford stack, and then it's just the fundamental group in that sense. The fundamental group as a stack. But I'm using basically the terminology, the earlier terminology of Thurston. Thurston, I think it's the orbifold fundamental group in Thurston's sense. Sorry? Yeah. Let me give you an example. Maybe that if you take, for instance, the moduli space of a principal polarized abelian variety of a certain genus. The inclination is to say the fundamental group is the integral symplectic group in 2G variables. But in the strict sense, that's not true, because there's a ramification, and that actually kills a lot of a lot. Yeah. Exactly. Yes, yeah, in that sense.
Yeah.
So the lattice associated to XL, the sublattice of the lattice of X associated to XL of the whole function.
No, because no. That's not. No, that's not quite the case. I take this double cover. Well, I omitted a couple of details, but it has that orbifold structure. So I look really at, let me say it like this. I allow, the orbifold, the fundamental group is of course also the Galois group of a universal thing, universal cover, right? And what you allow here for covers are covers which ramify a little bit, namely in codimension at least 2. So that's the notion that's being used here. I wish I had. He asked where to look. Well, maybe you can repeat it.
Yeah, where these structures could appear.
Okay, more questions? Yeah, go ahead.
Why the monster appears there?
Sorry?
Why the monster should appear there?
Why?
In other words, how
There is something there, but I cannot answer your question. I don't know, but I'm convinced there is something there because I didn't say anything about the proof. But what is very much being exploited is the structure of the monster, and this was intensely investigated in the 1980s by Conway and a group around him, and they found all sorts of structure. And it is almost as if that kind of structure was waiting to be used, because I encounter that structure in a very natural manner in the proof of that result. It comes with certain conjugacy classes of subgroups, and I told you this for a reason, because, for instance, if you take I is equal to 3, that's the codimension 3 thing that appears there, and then you see here an S4, and that S4, well, the monster has actually, or the bi-monster, I should say, has a very natural class of what Conway calls good S4s. And there are many of these miracles going on. But it's clear that there's a lot left to be understood here.
Is this density the model of smooth to be threshold or
well, in the end, it doesn't matter. In the end, I take here, as you can see, this is an open dense embedding, but I take the closure, right? So that's how you get these self-intersections.
Yeah.
Similar story for other eddy types like AQ before?
Yes, good question. Well, there is, for example, if you follow this constructor, you can replace, for instance, L3 by L1 cross L2. Then you get another 10-dimensional bulk quotient. And that and then the role of the monster, well, I didn't say what the kind of group that's associated to this 10-dimensional bulk quotient is. But in that case, this double cover construction leads you to a Chevrolet group of the field of two elements, orthogonal group of the field of two elements. Here it would lead you to a Fisher group. So the Fisher group 23. And, well, it would be also great if we encounter that group in algebraic geometry. Mm-hmm. And there are many more. I mean, I think it was Conway or Grice who called this this whole collection of finite simple sporadic groups that appear in the monster, the happy family. And of course, all members of the happy family sort of make their appearance in this setup.
Okay, more questions?
One last question.
Yeah.
In Allcock, when
Basa?
the result, do they conclude that this is simply connected in the usual sense, or that the orbifold by one?
Oh, no, only in the orbifold sense. Yeah, in the orbifold sense. I think the orbifold sense, that's the most important thing, right?
Yes, okay. So that in the orbifold sense, either you get monster times monster, or it's true.
Yeah, exactly. Yeah, two extremes.
Okay, so any more questions, or just because of the, I guess everybody is hungry now, right? We get eliminated. So let's thank the speaker again. Okay.